to the demonstration of Malware, a multi-agent reinforcement learning operating system. Okay, so the problem that we are trying to solve is the traditional system are centralized, having a single orchestration layer, which can lead to a single point of failure. And then there comes in unfairness. So if the job distribution is on the basis of CPU matrix, the nodes with the higher CPU matrix can always take the job, and the one lower suffer resource starvation, and our job is to have maximum CPU utilization, and the smaller nodes are going to waste. Okay, so we solve all of that problem in our this system malwares. So as you can see, we have three different agents running here, and these are connected to each other by a PubSub model via ZMQ protocols, and these are connected to peer-to-peer networks. Okay, and let me just try to submit a job here. Okay, I have submitted a job onto one node. So what it does is that node propagates that job to all other nodes. Then there is then as you can see, an option happens. So why an option? Because we needed an autonomous load balancing. We could not have a centralized load balancer at that would create a single point of failure. So we needed an autonomous load balancing. So we created a token system where each agent has some amount of money in their wallet, and they bid on the basis of CPU matrix they have, the trust score they have, and there are several other factors. So the decision which each node takes is there are three type of decisions that it can take, which is bid, forward, or defer. Either the node can bid, either the node can forward the job, or either the node can defer the job. So how it is decided? There is a 25 dimensional RL model trained on basis of lots of job simulations. So it decides whether this job can be performed by that node or not. And if the node has different capabilities, then that model learns that this node is always better for this job. So always that job goes to that agent. So and that's how the RL model comes into play and helps us in performing a very fast and low latency job distribution. Okay. And And then the other thing that we have is this trust score. So what this trust score does is every time there is a successful job completion, the trust score increases by some points, and every time there is a failure, it decreases. So if a node is having multiple failure, that means that node is compromised. So there is a watchdog that sees all the failure events of a node and reduces the trust score of that node. And if the trust score of a node goes below a certain point, that then node is quarantined and another node comes into its place, because we cannot have malicious nodes in our peer-to-peer network. So this is how transport comes into play. And then how it is fault tolerant. Okay, so whenever the bidding happens, there is a highest bidder, the second highest bidder, the third highest bidder, and so on and so on. So if the highest bidder that is performing the job, it fails to do its job, the job is checkpointed at every percentage. The job is checkpointed and saved, so that the second highest bidder can start to perform the job from the last checkpoint, so that whole job has does not have to be recalculated and uh, redone all redone over and over again. And there is and as I've already explained, like some nodes could have different capabilities, such as one node could have some hardware capabilities like turning the light on of something. So the RL model always learns that thing and always routes a job to that particular node which can do that automatically. And then there is one more feature, that is R predictive execution. So there are some commands that always come after one another, or the commands that we as a user we always run one after another. So what our RL model does, this is different RL model, what that does is it understands the pattern of the jobs of the command that you're going to run, such as let's say CPU compilation and then CPU execution. So if you're running CPU compilation and execution again and again, then that our RL model learns that you're going to do it again once more. So whenever you're going to run the compilation, our what our system is going to does, it is going to execute the next line, that is C++ execution in itself. So it is going to store that in its cache, and whenever you put that the execution command in the terminal, you get instant result, like from 4 second to 0.02 second or 0.01 second. Like it's instantly very, very fast. And for the testing, we have done all the type of tests that we could do. We have integration test, we have unit tests, we have system-wide tests, and lots of benchmarks to check. So what the thing is that centralized system are fast. They might be faster than this. And then there is a and that is a trade-off for having a secure and a fault-tolerant system where a job is always executed. And the RL model that we have inside, which decides whether to forward, bid, or defer the job, it it can learn from the structure of our nodes. Okay, so it can learn. So it has online learning enabled. So we on the basis of our structure and of how our nodes are, it can start to learn our whole model. Okay, so this was all about the MULOS, multi-agent reinforcement learning operating system that self-evolves, self-grows, self-heals, and always promises the job execution and fault tolerance. Thank you.